and I'm a founder of the Refuge project, which is a project that aims to build a decentralized platform entirely in Erlang. But these last 2 years, I've bought many applications that require a lot of HTTP connections to do a lot of HTTP connections. Some are using Couchbeam, which is a client in Erlang to talk to CouchDB using the HTTP API. Some are using just CouchDB, and in particular the CouchDB replicator. We'll talk more about that later. And others are doing a bunch of remote calls to local and remote HTTP services. One thing I've built for customer, mostly design, is an HTTP resource proxy. Every one of you know Amazon, and the Amazon website is doing a lot of call to remote services using HTTP or other techniques. But they have a lot of HTTP services on which they are binded, so they can expose some small parts of their engines in HTTP to the main HTTP server, which is Amazon.com. And I've built some stuff like this for customers, mainly as a gateway to access to CouchDB, filtering the replications depending on the people that you want to go, filtering documents, making authentication, etc. A lot of HTTP connections to CouchDB, a lot of HTTP connections also to S3 service to get blobs, to a QMP, Elasticsearch, stuff like this. Everything is in HTTP because we didn't want to use another transport, mostly because HTTP is so much easy to supervise and to cache, etc. So we are only using HTTP. So which means that we are using a lot of HTTP connections to these services. And the first version was written in Python, reusing some work I've done in Python, which is named tproxy and hashroot, which is an HTTP router. This stuff was wrote for European projects, and it's still in works in some firewall software. But it didn't work there. We have too much connection. We weren't able to scale enough in Python. We tried to solve that by launching a multi-process machine to scale, to launch multi-processes, multi-VM on machine, etc., etc., adding some network hardware. But it didn't work that well. So we took 3 months to rewrite it in Erlang, and it actually was working well, but wasn't enough too. We noticed some memory consumptions, a lot of memory consumptions. Some latency was making the connection crashing, and we have no way to supervise this connection, this request. Just in this proxy, things are quite easy. We are doing no keep alive. So once we have made a connection to an external services, we are closing the connection. And we are doing no continuous connection. So we're just doing some short live or long live connection, but that's all. Pretty simple. The other example that conducts me to examine, to analyze the other HTTP clients around was the CouchDB replicator. So I don't know if you know CouchDB. CouchDB is rapidly is a document-oriented database written in Erlang, mostly at the origin a clone from Lotus Notes, but derived since. And the CouchDB, one of the main features in CouchDB is master-master replication. So you are able to replicate the data between each node without having the concept of save or master, just master-master with conflicts handled. And the replicator is written in Erlang and communicate with other nodes using HTTP, because CouchDB, the main API of CouchDB today is HTTP. And the replicator is using Hybrid, which is the main known client in Erlang. Everything works quite fine when you are doing replication from one CouchDB node to the other CouchDB nodes. But I'm using the couchdb replicator in different ways. I'm using it as a replicator gateway mainly. So I'm replicating from remote nodes to another remote nodes, just doing HTTP connection. So when you launch a replication task, the first connection this launch is a listener that is listening for change on the source. And when a change happens, it fetches documents and attachments. Attachments are blobs attached to documents, just like you can have attachments attached to your mail. And it fetches the documents and its attachments and send back to the target. So I have actually at least 3 connections at any times for one document. So I have a continuous connection accessing to a couchdb source and a continuous connection to fetch the document, to fetch the document, and a connection to send a request to send the document to the target. And that's easy when you have 1,000, 2,000, 5,000 connections, but when you have 10,000 and more connections on the same nodes, it starts to be really hard, start to consuming memory. And the replicator is crashing far too often. Is crashing. Is also using a lot of memory at some point for an unknown reason yet. I didn't find the root cause right now. So we were doing until last month. We starting the replicator from time to time and launching multiple replicator without couchdb nodes on different machines with load balancing on them. But recently, I've rewritten the replicator to use Hackney to solve the situations, and it's actually working quite well. What is an HTTP connection? HTTP connections are mostly used today over TCP or TCP plus SSL or TLS. But it can also be over UDP. The main example is UPnP that you are using to access to your router to open a port, or UPnP used for video between your box and your televisions or whatever, and whatever you want to do. So you can do HTTP over UDP. HTTP, in fact, is just a protocol defining how you get headers, how you get blobs, how you can send headers on your connection. Headers are metadata in that case, and blobs and chunk of your data to a remote source. You have right now 3 main versions, maybe 4 versions of HTTP used. One that doesn't exist yet. So you have HTTP 1.1, which is the one actually used everywhere. You have Speedy that is used by some server, which is I will go back further on that, which is used, which has been created by Google and is the ancestor of HTTP 2.x, or at least defines some stuff that will be used in HTTP 2.x. And the old version that is still in use, HTTP 1.0 versions. In Erlang, you have mainly 4 HTTP clients. The first one is HTTPC, which is the HTTP client distributed with Erlang. So you don't have to install anything when you install Erlang, at least when you're not using Debian or Widget. HTTPC works quite well under a lot of the HTTP 1.1 spec. You can even multiplex connection using pipelining using HTTPC. You can stream your response, but something is missing, or I didn't find in the doc at least. You can't stream your request. You can stream a response, but you can't stream a request. You can just send binary or IO list or a file using the sendFile API, but that's all. iBrowse, which is the oldest one after HTTPC, of course, which is doing a lot, is also doing pipelining, is also doing a lot of the HTTP 1.1 spec. You can stream a request, you can stream a response, you can do a lot of things. The only things I notice with iBrowse is quite slow when you have a lot of connections at some points to open a new connection or to get a new connection from the pool. And again, and I'm pretty sure now that this is mostly due to the message passing used to under the request. But the memory consumptions get pretty high when you have a lot of connections at the same time. And pretty high, I mean, on a machine with 8 gigabyte and only doing HTTP connection, you can hug it all the memory in one day when you have a lot of connections. So we on the machine previously we were restarting the machine every day, the VM every day with the couch replicator. LHTPC, which was written by for the Erlang solution company, I think 5 years ago, something like it. But when I look at LHTPC 2 years ago, it wasn't feature complete. Philippe, which was an older couchdb developer committer, has the same idea as me, and look at it and actually change in Couchbase iBrowse for LHTPC. And he took a different patch from me, so I decided to write my clients. He decided to put some patch on LHTPC, now useless because Couchbase is not using anymore LHTPC. But he has done some patch, adding proxy feature, adding the possibility to have multiple of connections, etc., etc. So LHTPC today is quite feature complete. You can stream a recursion, you can stream a response, but you are still missing some feature like the possibility to monitor a connection, like pipelining. It doesn't exist, stuff like it. And Hackney, we talk later about that. This is the clients I wrote after having a look on the 3 main clients. There is another one not really used in production today, which is Gun, written by Loic to test mostly SPD, which has an interesting design. I will come back later on that. So what I'm trying to solve is C10,000 connection problem or C100,000 connection problems, but on the client side, not on the server side. And when we are speaking about connection, we are speaking about HTTP connections that have their own challenge. We are always fighting with system limits, and particularly the number of file descriptors. So each time you open a socket, you open a file descriptor on the systems. And the file descriptor takes around, I don't remember the number now, 24 kilobytes, something like it. No, less. Don't remember. Sorry. It takes some memory. The number of file descriptor is limited. If you are on a 32 bytes systems, it's limited to 16,000 file descriptor, more on other systems, but it's limited by default. And you don't want to increase a lot your file descriptor because you will hang your machine very, very fast. And file descriptor are really important on some systems. If you are working with OS X, you will notice that your connection will lag a lot when you are doing a lot of I/O write or read on your disk, because both are using the same system in the kernel, in fact. And so when you are doing a lot of write or reads, you won't make a lot of connections. And when you make a lot of connections too, you will have some latency to write on your disk, which is something that you don't really want sometimes. The RAM, the memory is also limited, of course. So when it's limited, it's reused. So of course, to reduce the number of connections, you can cache locally your HTTP connection. So when something, when you have passed your HTTP request, you cache it on the server or locally. But then you at some point it will use a lot of RAM, so you will decide to use a server to distribute your RAM, and then you will open new connection to distribute your server, and etc., and you enter in a vicious circle, and that won't finish. Using HTTP, you don't really need to cache locally, because HTTP offer you, when the server is well designed, offer you the possibility to check if the content that you want to download is new, or the server will make sure to not send to you the body, at least. So you don't really need to cache HTTP when you reuse the connection. Because the real things to do, in fact, when we are speaking about connection, this is reusing, just like in ecology, rather than trying to launch more and more connection, more and more machine, which is not possible depending on your budget. You will try to reuse what you have already. So rather than launching a new connection, try to not close the connection and keep it somewhere and reuse it the next request. And this is pretty easy to do that with Erlangs, because Erlangs offer you some nice possibilities to control your sockets. You can get the events, the activity of your sockets very easily by, you won't see anything, by setting the socket to active ones. So here this is an example. So I've done a request with my sockets, and then I finished. I know by HTTP that I can keep alive this connection. I got a keep alive header. And so we'll decide to reuse this connection for the next call and put it in a pool. Here, this is some pseudocode that that can happen in a pool. So the first time when you check in your socket in the pool, you set this activity to once. So it means that you will wait for one event of the socket. Why you are doing that? Because you want to know if your socket is closing at some point, because it has waited too long on the pool, or because the server, the remote server has closed the socket, whatever. You want also not to keep too long the socket in your pool, so you set a timer that will send a timeout event with the socket. And when it happens, you remove it from the pool. And if someone wants to check out the socket, so reuse the socket for the next request, he will send a message, a synchronous message to check out the sockets. And we are passing the control of the socket to the new process, and we are sending it the socket, etc., etc. So because of that, you can really control your sockets. Of course, this is some pseudocode. The main way to use it is using a gen server, for example. In the gen server, you place your socket in a dict or in ETS, and each time, so you check out your socket, you put the events, and you will receive it in the under info method of your gen server, and remove it or not from your pool. Or some clients like Gun server or like HTTPC are not using a pool, but are keeping the process open and try to pass the request to the open process. And if it exists, then if the socket is still open, pass the request to it. All the clients, whatever they are using one technique or another. iBruise and HTTPC and Hackney are using a pool, and HTTPC is not using a pool. Of course, reusing a connection is not open. You can put some limits in your pool, saying I want to only store 100 sockets. But it lets you only one possibility to check when you put your socket in your pool if you want to keep it or not keep it. But for the rest, you just starting new requests without limits. You can keep a limit at some point and say, I'm stopping to open a new socket. But then you don't know. You have different strategies. So you can say, I'm stopping to open new requests, and I'm dropping any connection, any new connection. I'm saying to the one that you want to open a new socket that this is not possible, or you are queuing any new request. So you are making the process trying to make a new request. You make it wait on that, or you are sending it, and kill maybe a socket that took too much time in your. You have different strategy. And today you can only do it with two. Mostly do it with two libraries. So there is an LHTTPC fork. You don't see the link, okay? So you have an LHTTPC fork that is using disk_count from fair, and hackney disk_count, which is propose you to use disk_count, which is a queuing system with a different strategy on that to use it as a pool. So in this system, you can launch a lot of requests in parallel and kill them when you want. Limit the number of requests you want in parallel, the number of concurrent requests, and queue some or just drop any new connection to it. This is while for LHTTPC you have to use fork. For Hackney, this is pretty easy because you can put a new pool. You can write a pool and add it and tell Hackney to use your pool code if you want. This is pretty easy. You just use a pool backend, either by default for all the pool, or when you want to open a new kind of profile, you can set a pool backend and use this pool backend, create this pool backend. So you can fight with the file system limits, and one of the other system limits, and one of the other limits is memory usage. Memory consumption can be big because when you are doing a lot of requests at the same time, you are also launching a lot of data at the same time. And I will talk that about a little later. But when you are launching a lot of binaries at the same time, the garbage collection doesn't happen at the same time. So your memory consumption continue to increase, and at some point can be really big. So the first thing that you really need is a client able to stream when you receive, of course, your response, but also when you send. So you reduce the size of the chunk you have in memory at some time. And like I said, HTTPC is not able to do that, sorry. So we have system limits, but one of the challenge when you are doing when you are handling connection and when you are doing HTTP connection too, is that a network can be hostile. A connection can crash because you made an error in your code, and you want to isolate that. You don't want the connection crash all other connections around. And this is it can be handled in Erlang. So you want. Connection can crash at any times, so it means that it can crash when you are connecting to a server. It can crash when you are sending to a server or when you are receiving to a server. And you want to be able to handle all these cases. A connection can be slow or too fast. Sometimes you have some network latency, or it can be too fast. Your server is not ready to accept your connection, your body, your payload, or your headers. Mostly your payload. And HTTP is able to propose you a way to handle that. But back on the latency, HTTP 1.1 is a very buggy protocol. He passes a lot of times in the network. So the first time a client connects to the server is launching a SYN request, which is a TCP message, sending to the server to see if, to open the connection, to start to open the connection, and if the server acknowledges, it starts to send a request and saying here, I want to get the CSS resource on the HTML path. The server process takes some time. During that time, your client is waiting, and it can be 40 milliseconds. And then your server decides to send a response. Again, it takes some time. Your client says at this point that he can resave. He can send the header to the server. So he's starting to fetch the final response from the server. Again, it takes time, and then you close the connection. So during all that times, you have a lot of chance that something happened on your network, especially when you are doing a lot of connection. So it can be on your network, or it can be on your network card, because your network card is a big bottleneck. Whatever. So at this point, you can either here on the SYN request get a connection error, a connection timeout. So you need to be able to handle that. Here, when you are starting to resave, you can have the connection can crash too, and you need to be able to handle that. And while on the server, this is pretty easy. When your connection crashes, you just let it go. OK, it's crashed. This is not my problem. This is the problem of the client. But when you are doing a request, you are doing a request for some reason. And depending on your policy, you can say, I'm drop it, whatever can happen. I can accept that the connection is not made, or you need to be able to handle that later. And this is quite more complicated on the client side, because while you are doing a lot of connection, you need to be able to handle a lot of events at the same time. For the expect 100 continuator is interesting in HTTP. It basically means if your client is able to handle that, your client is saying to the server, I will wait for you that you tell me when you will be able to send me the body. So I'm sending an expectation to the server. I'm expecting that you are sending me the body sometimes. And the server takes its time, process, do something, check the response, check if the payload is actually local to his server or replicate it, whatever you want to do. And when he's ready, he's sending back 100 continuators to Hackney, saying, it's OK, you can fetch the body to the client, and it's OK, you can fetch the body, and the client starts to fetch the body. Then you make sure that you can reuse efficiently your connection and not sending too fast. In HTTP 1.1, reading header is a big bottleneck. This is a big part in the parser. Your parser needs to be fast when you are reading headers. And the default parser in Erlang is not really that fast to read headers. This is in C, OK, but this is not really that fast. This is not also, you can do it in Erlang, can try to optimize it, but this is not also that fast. Because in Erlang, we are buffering the sockets. Where in C, you can read byte by byte your header and then pass really fast. So in Erlang, there is Erlang-HTTP, I think, which is an if over the giant parser, which can be useful for that. I never try right now because I don't have so much headers. But when you have a lot of headers, the header is what is taking the more time when you're passing an HTTP request. Sorry. And you need to supervise your request for the reason I said. You need to know when you request timeout. You need to know when you request stop to resave or whatever. So you can garbage collect more often your connection, or just retry your connection, stuff like it. So I try a lot of clients, and I decided to design mine, to write mine, because it was faster than hacking the other. Trying to change the logic on an application can take some time, more time than writing the code by itself. So I decided to write the code. And all clients right now who are using HTTPC, LHTTP, hybrids are using these patterns. So when you want to make a request, the first thing that the client does is opening a new process, and this new process will keep the state of your request. If you need a buffer to continue to parse your request, or if you need to keep some headers, etc., everything will be maintained in this process. And I think that one of the other reasons for that is that it's also isolated your request from the other. So if the request crash here, you won't touch any other request, or not even touch your clients. At least we could think about that, but none of them are really using that as a process. So they are all waiting synchronously for this process, the message from it. The message passing is used to dialogue with this process. So when you want to send the data to the socket, you first send a message to the process, and then the message is sent to the socket. And the socket is sometimes maybe fetched by pool. In Hackney, the first version was initially just doing that. It's not launching a new process. It's just creating the socket, put it in your record, and return to you a record, a stat, an opaque stat, maintaining the socket, etc. So if you see this API, this is the first version. You make a GET request on find path, and you will get these context objects. And when you want to receive a chunk from the body, you get a new context, etc., etc., etc. So it was working, no message passing, but the API was really painful. After some time, you have a lot of context to change. And when you wanted to change a pool here, you needed to create a new context, or you need to wrap it to have a function creating your context each time. So it was really painful. So I decided to redesign that and saying I will only get a reference. My first thought was to make like the other, launch a new process. So I opened a ticket on GitHub asking for what they think about this design. And I have a lot of people coming back on that and saying it was really a bad idea to launch a new process because of garbage collection, etc., etc. And there were some interesting links about that, saying what are the problems with message passing and the memory consumption. So I decided to not use message passing and to not open the process. Keep the same system that you have in Hackney version 1, but I still need to remove that context. So I put a ref, and this reference is you have one unique reference ID by request that is done, and instead of storing the socket in the process and speaking with the process using message passing, I'm storing the state, the buffer, and the little headers I need in ETS. So here I have no message passing, and I'm able to give the control of the request to another process without using much memory, because ETS uses its own term storage. And this is very fast. I'm just speaking to the memory. I'm just storing a state. And ETS offers you some interesting possibilities like the read concurrency option, which allows you to read concurrently your ETS very fast. And you can also use the write concurrency option, but I didn't use that. Well, I was here because I thought it was still useful to be able to receive asynchronously your response. I let the possibility, just like for the socket, to activate the event for a socket and say, now I want to receive my message asynchronously. So I'm launching a new process that will, so once I send the request to the HTTP server and the HTTP server start to launch a response, at this point I'm launching a new process. And this new process will still talk to ETS to store the state, but is receiving the message from HTTP source and sending me back even to this process. Which means at this point, I can also move, change the process that received the message, pass the control of the message to another process. But it also means that I can say, OK, stop. I don't need to receive any more asynchronous that I have everything I wanted. So go back to my synchronous modes and continue to reset my sockets. And because I didn't want to let a socket running in the wild, if something happens, if a crash happens, I want to be able to garbage collect too. I'm supervising both the clients actually accepting getting the request results, and a supervisor actually monitoring the async process. So if any of them crash, I'm just getting back in the Hackney manager, removing the ref and doing the emptying the buffer, removing the ATS record and whatever you need, so it makes the garbage collection a lot faster. So let's see, yeah. So because what happens when you are sending a message to your process, you are you are copying data from one process to the another. You are not copying data if your binary is greater than binary size is greater than 64 kilobytes. You are only passing a reference, and then your binary is stored on another memory allocator. Can be an mmap or malloc, and the reference is kept around. So when you are copying your binary from one process to the another, each process increase the count, the count of your reference. So you have reference counting, which also means that the reference is kept around until all the processes that have access to that have been garbage collected. And until they have been garbage collected, your binary stay in memory. If you forget to remove a process, if you have a loop running or whatever, or if you have a lot of connections at the same time, you have a good chance that the garbage collection won't happen at the time you want it, and so the memory increases a lot. And this is why I'm trying to remove the Hackney, the garbage collection. So it's actually solved that my replicator is more efficient. I don't have to restart the machine. I don't have any memory hogs now using Hackney. I have a simpler API too. It can easily handle multiple connections. I'm actually not get over 20,000 connections, but I think you can. Never try. Now, like I said, but I'm running out of time, I think. Yeah. HTTP2 is designed for Erlangs. In HTTP2, you have message passing built in HTTP2. So stream are bidirectional. You can multiplex your connection. You can send multiple requests in one stream. And you actually just pass message. So when in HTTP 1.1, you have to detect if you are fetching a status from your HTTP connection or an header for your HTTP connection. Here you are just sending a clear message saying this is the header. You are actually parsing headers. You are actually parsing the body, etc. So because of that, I'm thinking to go back to a process handling the connection, because one process could handle a connection and can multiplex for one process all the requests to HTTP2. And because I don't want two systems, trying to abstract that for HTTP 1.1. Soon, not on Monday because I'm coming back in the flight, but soon there will be Hackney Connect, which abstract in a library all the connection manager from Hackney. So you can write, you can use it for anything. And there is also a connection event handler, so you will be able to subscribe to any events of your connections and doing logs or whatever. And while I'm here, adding WebSocket support. Okay. Oops. Thank you. If you have any questions, if you have something. No. Okay. Thank you. Thank you.